447. So let me give you a second on these ones, starting with vocab and then moving on from there. Can you guys see it? So 1 is the dividing out technique. That was from our notes. 2 and 3 and 4. Number 6, 0, 1, and -2. Number 10, the final answer was -7. This was the dividing out, or hopefully you could factor. Factoring would be a lot easier. But some of you might have done long division, and you should have also gotten to 2x minus 1. Plug it in, plug it in. Number 12 was a little rough, so you might have needed to do what we did in our notes when we had x cubed plus 27. This was super similar. It was a cube and a perfect cube. You didn't have to do the factoring method. You could have done the dividing out method. You just would have needed, guys, if we put this in the box, we wouldn't have just written a cube plus 64, right? What would we have written? If you were dividing, because a lot of you didn't know how to factor that.
A cubed
Plus
0 a squared plus 0a plus 64.
But didn't we do this in our notes?
Yes.
We did one super similar. And when you divided, it went in evenly, and you should have gotten this guy. And then you just plugged in. And the final answer should have been 48. How are we doing? Give me a thumbs up if you feel like we kind of got it.
We're good.
Give me a thumbs in the middle if you're like, it's a little rocky, but I'm not lost. Okay. Rocky Balboa. Get some theme music going, huh? Okay, let's scroll down. Party pooper.
Sorry, we always need a theme music.
Oh, okay. 16 and 18. We have a radical one with a conjugate, and we have a complex fraction one. Now, guys, if you get really, really good at simplifying complex fractions, you could maybe make this mental jump also. But otherwise, this is a really hard mental jump. This is a lot of mental math. Like in my mind, because I've gotten my method down really good, I could make that jump, but most of you couldn't. So real quick, what you should have multiplied top and bottom by down here. Did you guys find your stuck denominators?
Yes, ma'am.
You should have multiplied top and bottom by 8 and x minus 8. By 8 and x minus 8. And when you multiplied by both, this first distribution, the x minus 8's cancel, and the 8 is left. The second, the 8's cancel, and the x minus 8 is left. And maybe that can show you why or how they were able to say the 8's left, the x minus 8 is left. There's a plus in between. Sweet. And on the bottom, the 8 gets put together with the x, gets put together with the x minus 8. So they did my trick. That's how they did the mental math. But for most of you, you should probably show the math to get there. But then at this point, the 8's cancel, whoosh, the x is reduced, whoosh, plug it in, dun, dun. Uh-huh.
So if we did make the jump, should we still put the work down?
I would at least show what you multiply top and bottom by. Because you have to get really good at that trick in order to be able to make that jump properly every time. Does that make sense?
Yeah.
Pause. Look at your work. Are you guys rewriting limits? If you're not, write it in. Maybe even write it in colored pen, because you need to know for the quiz to rewrite the limits. Okay? You need to know for the quiz to rewrite the limits. Abby? Mm-hmm. Yeah. Well, -2 plus x, remember addition can be commutative, which means we can flip order. So -2 plus x can become x plus -2, which is x minus 2. Because in this one, the 2 is negative and the x is positive. The 2 is negative and the x is positive. So technically, if you like it better, you could have written it x plus -2 and been like, oh, those are the same. Does that make sense? So then I reduced, we should say I went there. I didn't really do the equals. I didn't show the top and bottom. I simplified this guy to be negative 2 plus x, which can become x plus negative 2. Those two can reduce. Now you have 1 over what's left. Plug it in, plug it in. Jaden.
For 18, for the denominator, for the 8 and 8x minus 8,
Yeah.
they multiply it by the 1s, so they also have to multiply it by the bottom of the x.
Yes. When they multiplied on top without rewriting it all, and it distributed in, we got rid of and we left the 8, and then we distributed again and we got rid of and we got the x minus 8. But there was also the bottom, which is why the x isn't alone. He has the 8 and he has the x minus 8 as well. So they both had, because if they didn't multiply, then it would have never gotten to be that big old long guy that you see down there. But you don't need to multiply top and bottom here. You're multiplying 1 to the numerator, 1 to the denominator, and the numerator is coming in. And if it helps just a little bit, which I guess I didn't show the long version yesterday. Just in case it helps. I think this is what you're asking, like multiplying top and bottom, right? Okay. So this is all together. That's fine. This is technically over 1. You can think about it like that. So on the bottom, I just get that 8 with the x minus 8. But on top, when I multiply, technically, if we were to write it out, I'd have 8 times x minus 8 over x minus 8. So that is me multiplying these two together. Just in my head, I then canceled to get just the 8. And then this one, 8 times x minus 8 all over 8. I did that in my head and just left x minus 8. Does that make sense? Yeah. Okay. You guys have more evens though, yeah? Okay, let's keep going. Okay, now once we get to 48, that's that new thing that we probably got stuck on, 47, 48, 49, 50. So let me give you a second to go ahead and check these. Hence why the limit does not exist. Now this stuff is the new stuff, right? So here's the dealio. Let's pause on this. The homework that you guys had due for today. If you want, you can go ahead and put parentheses around 47, 48, 49, 50. Technically, that is what we need to cover today. That's section 12.2b that leads into section 12.3. So really what we're going to cover to help you guys out with 47, 48, 49, 50 is exactly what you need for section 12.3. So we'll do both at the same time. So let's go back to our notes. Maybe we'll even get to do one of these evens all together. That way you have a homework problem already done. That sounds good? So let me go ahead and get another page in here, and that way we can go grab, let's do number 50. Isn't the later one usually the harder one? Okay. So I'll leave 48 for you guys, but let's grab 50. And that will be the example that we will end section 12.2 with, but remember, this is also what introduces section 12.3 at the same time. Let me actually grab the whole little piece. There we go. Okay, so we have him ready to go. Let me get my highlighter out. Oops, there we go. Okay. So here's the page that you guys were writing at the very beginning of class. The last topic really that we're going to be covering, besides maybe a couple terms, vocab, things like that. Back to the difference quotient. So the difference quotient, it's been a while since we saw this guy. And we definitely never took a limit of him because we didn't even learn limits until chapter 12. It's been a while since we saw this guy. We saw him way back when we were practicing function notation and we were doing f of and trying to figure out how to plug in. So here's a quick reminder of how to simplify the function notation, how to actually get this when given an f of x. So before we can ever take the limit, we have to actually get the difference quotient all nice and plugged in for a function. We have to get the difference quotient all nice and plugged in for a function. So a couple reminders. First of all, the very first thing you should do when trying to get this guy all nice and plugged in so that we can take a limit is to find f of x plus h. He's one piece of the puzzle. Let me go ahead and get rid of that guy because he's kind of just in my way. And we have a different example that we're going to do for the second part. So f of x plus h. The first thing we have to do is plug x plus h into the argument of f of x. Remember, every function already has an input. Every function already has a place where a quantity or a piece of data or something is supposed to be plugged in. So when you see f of x equals x squared minus 1, it says f of some sort of input is whatever you input, square it, and then subtract 1. So on this one, if we're supposed to find f of x plus h to even get close to solving this problem, okay, f of x plus h says take the formula up above, input squared minus 1, and what is the new input as soon as I have x plus h? Yeah, it used to be x, and now it's x plus h, so I just put that in instead. It used to be x was being squared, but there's a new input in town. X plus h is now here, so okay, fine, plug in x plus h. Plug in x plus h. So whoever the input is, whoever the of is, I just plug straight in. This is back to function notation you could find in function notation chapters 1 or 2. Somewhere with function notation we did a lot of examples of just how to plug in, not limits, of course, we weren't there yet. It's h approaches 0 is the limit that we're going to need to do. The nice thing is this is going to be given to you. It's not something you have to memorize. I mean, it is something you could put on your formula card for the final, but like on the quiz, it'll be given to you. This is what you're needing to plug into, is this formula. But before we can even get this formula to take a limit, we got to get this guy first. Kiddos, don't kill puppies. How do I square a binomial? FOIL. I'm going to end up with x squared plus 1hx plus 1hx is plus 2hx plus h squared minus 1. How do I get that? We've been working on it all year. X plus h times x plus h. First, outer, inner, last. First, outer, inner, last. So if you need to, off to the side, maybe take a second to go ahead and actually do the foiling if you can't mental math it. Remember, no judgment if you can't mental math it. Yeah? Foil it up. Now, do we have f of x plus h? And the answer is yes. So therefore, this guy, check, we have him. But who else do we need? Wait, don't we already have f of x? He's right here, right? So check, we have him, we're ready to go. So let's go ahead and go to our formula and say, okay, I need the limit, according to the formula, as h approaches 0 of. Every time you can put over h. That's just an automatic. Does not depend at all on the function that you've been given. Joel, hang in there, bud. F of x plus h, we just found him, so plug him in. That's x squared plus 2hx plus h squared minus 1. But that only covers this first part. What has to come after f of x plus h? Minus, and then the f of x, which is x squared minus 1. So just in case, you need to see some like color coding. I need the f of x plus h, which is this guy, which I found right here. Then I need the f of x, which is this guy, which was given to me in the very beginning. So really I'm just plugging into the formula. Take the f of x plus h after you get them, subtract, take the f of x, which they gave you. Now guys, if you were to plug in right now with the difference quotient, always, 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 you're taking the limit as h approaches 0 in section 12.2, the end in section 12.3. And if you plug in 0 to just the h spot, do you realize x plus 0 is just x? What's going to happen with f of x minus f of x all over 0? Which is why I had you guys FOIL this guy, because we needed to keep going. Which is why I'm going to have you guys try to simplify, because we need to keep going. So what can I do up top? Do you guys see anyone that looks even somewhat similar? You got it. So let's distribute that negative to make everything all legal. And as you distribute the negative, don't you notice the x squareds cancel? Then don't you notice the 1's cancel? And I have an h on the bottom. We haven't reduced top and bottom yet, and that's what we really love to do for any sort of 0 over 0 keep going. Man, I wonder if I can somehow reduce an h away. If you take the h out of both, because it's a common factor, I'll get 2x plus h all over h. I can reduce the h away. Now I know it's a little weird because we have the limit as h approaches, so we're only plugging in for h and not for x. But guys, what plugs in? What happens when you plug in? Because so far, rewrite the limit, rewrite the limit, rewrite the limit. It'd just be 2x. The limit's gone because we plugged in. 0 for who? 0 for h. That's what they told me. All right, fine. 0 for h. There he is. In calculus, this is what we call a derivative. So let's go try the homework problem. The second even one. Sound good? What do you guys think our very first step is going to be? I don't know if we could simplify right now. There's no like terms. We do want to plug into the formula. I think, Jackie, was that you? We do want to plug into the formula. We need to plug in first. Does that make sense? We need him. And if we do it all at once, some of you could do this all at once and do it all in one big old plug-in. But for a lot of us, it's going to be easier to find this guy first, then plug in. So let's go ahead and say, okay, I'm not quite ready to do my limit yet. I'm coming back to that in just a second. Before I get to my limit, I need the f of x plus h. Okay. So where's the input go? Right there. So f of x is equal to 1 over input minus 1. And as soon as I have f of x plus h, who's my new input? Good. So he goes in the input spot. Is this going okay with function notation? Whenever the thing in the parenthesis changes, I need that spot to change in the formula. Okay, good. So I get 1 over x plus h minus 1. Combine like nothing. Oh. Wah, wah, wah. Okay. So I need my f of x plus h, which I just found. Who goes in the next spot of my formula? Ah, that was the guy I had in the beginning, right? Has section 12.2 prepared us for what we need to do next? This is a difference quotient. It's going to be a 0 over 0. Keep going. We know it is. Every difference quotient always will be. So what am I going to multiply by? You saw there are two different denominators, right? Okay, so let's get them up. It's okay. But is the process the same, though? Yeah, I'm stealing my stuck denominators. It looks complicated, but the process is the same. It looks complicated, but the process is the same. So then, as you guys notice, hopefully, you practiced this last night. If you did homework. If you didn't, well, you're obviously not going to be so good at it if you weren't practicing. Some of you are already seeing, hey, I know what happens when I distribute these common denominators. One of them cancels, and one's left. And then when I distribute again, the other one cancels, and the other one is left. And on the bottom, I just leave everybody because I'm really hoping someone reduces. Chris is already seeing, wait, that numerator, I think there's like terms. If only I could kind of, not kill a seal and distribute some negatives. So I have x plus 1. Negative. What cancels up top? X's cancel. And? Who's the only guy left? So what's true about that negative h over h? Can I reduce that? And Joel, this is like the one yesterday. So when I have both of these on top of each other, I can reduce them, but what's remaining? Negative 1. Good. I have a negative 1 remaining. So then does it make sense why I'm going to write negative 1 over, right? X plus h minus 1 times x minus 1. What do we always try to do if we can reduce top-bottom? What's next? Plug it in, plug it in. And the only thing we're plugging in for is, who's the variable? H. And what am I plugging in? 0. Nice. I'm going to end up with, I stop writing the limit because I'm plugging in, negative 1 over 0 is just x minus 1. Oh, hey, what's true about that? They are the same. We could FOIL, but you know how they usually like it all nice and factored? So we'll just leave it factored and say, negative 1 over x minus 1 quantity squared. Now, here's a quick little plug for calculus. This is where calculus starts, is solving these crazy things called derivatives that we haven't talked about yet. I mean, all we know is that there's this difference quotient and there's a limit, and I don't know, maybe it means something special because she keeps talking about it with calculus. Okay, fine. But these are things called derivatives. We start by solving this using this big old what we call limit definition. It's one of their very first forever cards they have to memorize. But then pretty soon, they start learning basic rules. And the basic rules allow them to go from here to here in about 10 seconds. Not doing any of that work. And it allows them to go from here to here. Well, yeah, they have to learn a couple more sections, but eventually in about 10 seconds without any of that work. There are shortcuts, but not to this process. There aren't shortcuts to this process, and this is where they have to start too. But there are shortcut rules that allow them to make a jump from here to this very important thing called a derivative here. But there's just a lot of content that needs to be covered first to get them to those shortcuts. Now, before we go into section 12.3, which is where we're headed, I'm going to give you the short and sweet version of it. I'm going to tell you guys that you can call this final answer to this very special formula f apostrophe of x. We call it f prime of x. Then down here, it is the answer to what we call this limit definition or a limit of a difference quotient, but it can also be an f apostrophe x, or we would call it an f prime of x. Let's go figure out who that f prime of x really is. Section 12.3. This is a perfect segue. 12.2 actually started or taught you how to solve what you need for 12.3. That's why I was like, let's not go to 12.4. It actually goes to something new. Let's end with 12.3. That's basically like, let's just give you a little baby peek at what you just did. Just going to give you a baby peek at what you just did. Now, guys, do you need to practice that difference quotient thing on 47, 48, and 49 tonight? Yes, you do. Yes, you do. Practice will help you improve. Can we go over a couple questions tomorrow on the 12.3 homework, 12.2? Yeah. And just a heads up, I very well might, at the end of class, I have your homework document open in the Google Drive. I might take out a few problems just to let you narrow your focus. I'll go ahead and tell you now, tomorrow is going to be a group quiz for a couple reasons. Tomorrow's quiz is going to be a group quiz for a couple reasons. A, some of you might have guessed it from last semester. B, some people have been just trying to catch back up after having to miss for APs. And some of you feel that, and you're like, that's a struggle. But that means that those of you guys that have been in class every day need to be ready to help. And those of you guys that have been gone need to not be a dead weight, so you need to actually have your notes up to date and have homework practice. Group quizzes are good as long as everyone somewhat contributes and doesn't drag it down. Does that make sense? Okay. So everyone should be back tomorrow. There's no AP. The only exception are my ones that are going to be in the assembly, which is Joyce and Ruth, Lainey, and AJ. Poor AJ.
Juice.
I know. I was doing the breakfast this morning for senior leaders. Struggle. So those 4 will be in the assembly. But if you guys notice, isn't that kind of like a group? So they're going to take it as a group on Monday. They're going to take it as a group on Monday. Now that also means that some of you guys are like, oh, but my group, some people might be missing. We'll join you together with other groups. So like Maria and Joel will make sure that we put you in other groups. That way you're not like on your own. Maybe we even have Jackie and Jaden join together with Maria and Joel. If someone's absent tomorrow, obviously we'll figure something out and try to join some groups as well. But does that give you guys a little more pressure for being ready tomorrow?
Yeah.
Does that mean you have to know everything? No. Does that mean you necessarily have to have everything memorized? No. But do you need to at least be practiced up?
Yes.
Does that make sense? Okay. Nick? Probably 25 points. That's pretty normal on a quiz. 20, 25. Probably be a bonus opportunity, and you are allowed to have your calculator out. But some of them, especially 12-2, I'm going to want to see by hand work. Is that cool? But you can check in a table, make sure you got the right answer, yeah? Yes. But if you notice, and maybe you didn't pay attention, but I said 12.2, what we just covered with the limit of the difference quotient, is really the only math you need for 12.3, which is nice. Okay? So here's the idea of 12.3. Here's the idea of 12.3. One of the fundamental foundational problems that calculus, in a sense, was created to answer. One of the fundamental problems, in a very, very simplified graphical way that you guys can kind of understand, was the dilemma of how do we find a tangent line at a point? And we kind of already saw this with the parabola way back when, and there was all this crazy geometry with distance formulas and foci and all this jazz that we had to use in order to find that tangent line. But actually, it's a much, 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 much simpler way of finding it that does not only parabolas, but works for any possible curve that you could be given. Now, I know a lot of these look like parabolas. This is like an exponential. That could be some sort of weird cubed root function. That could be like a quartic function. Anyway, this works for any function. Going into tons and tons and tons of depth about how this guy's increasing with a positive slope, decreasing with a negative slope, or bringing in all these applications of tangent lines or really instantaneous rates and how fast something is changing right at an instant. That applies to econ and physics and chemistry and all sorts of different fields of study. Without going super crazy, just saying, hey, there's this thing called a tangent line, and it was always a dilemma trying to figure out how to find said tangent line, because how do we find equations of lines? We need at least how many points? No, I'm just putting out my hand. How many points do you need for a line? Just 2. Just 2. But a tangent line is defined to only hit at, that's the dilemma. A tangent line only hits at 1. So the dilemma is, how are we supposed to plug into, for instance, a point slope version of a line if said point slope, yeah, we only need 1 point for the point, but for the slope, what do we need? 2. For the point, we only need 1. That's great. We can use the point of tangents here, the 1 point that it hits a graph on. But the dilemma is the slope. We need 2 points. Well, if a tangent line is defined to only hit at 1, then how can we do a slope if we don't have 2 points? I mean, we could try to draw them and get really, really, really good at drawing them. And if we get really, really good at drawing them or steal maybe a graph that a computer generated for us, then maybe we could approximate it. And maybe we could say, oh, hey, we see the tangent line. I know this point is the point 1, 1. And I can look on this and say, oh, look, it seems to go up 2 and over 1 to the point 2, 3. We see going 2 over 1, maybe we can use the rise over run to say, ha ha ha, I found the slope of the tangent line. But that was very approximate. And you had to have a picture first. And you had to have a very, very accurate as far as what the tangent line would look like and exactly where it would hit. And that's not going to be very practical. Kind of works for eyeballing, I suppose. But it's not very practical to actually, especially in problems that need very, 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 very precise measurements. So if that's not good enough, it's not good enough just to eyeball it. Do I need to dual page it? we need to have a better process. And the better process involves using secant lines. Using secant lines. Now guys, you don't even need to label the graph that you see up here. Don't really stress about all the different labels in the graph. I will zoom in so you can see it. The long story short is the slope of the secant line, without going into tons of depth on the theory of it, the slope of a secant line which does not skim, which cuts through, you guys saw secants in geometry. Secant lines cut through. That's not a tangent line. A tangent line is nice and skims. But the slopes of the secant line can actually be written as the difference quotient that we've seen first semester and then just last section. Slopes of secant lines can actually, bless you, bless you, bless you, bless you, be summarized. The y2 minus the y1 over x2 minus x1 can actually be summarized with the difference quotient. And I think most of you should have this page over here. So I'll zoom in so you can see the picture if you want to see it. The long story short, that thing that we've just been calling the difference quotient actually applies to secant lines. Actually applies to secant lines. Because the secant line says, well, if you go over a certain amount of h, then we can start from an original x and say, oh, hey, this will be x plus h, and then we can go ahead and plug in to get our y's. And we can actually do a little y2 minus y1 over x2 minus x1. The x's cancel, h is left. The difference quotient is a secant line. Now, hold on. The secant line is not a tangent line. That's bad. But guess what's going to happen if I have h? Wait a minute. Didn't we just solve one of these? Or two of these? Limit. We want the secant lines to go towards the tangent line. Limit. What was the limit that was in front of the difference quotient that we were just solving? The limit as, what's h stand for in the picture? The distance. What's going to happen if this gets smaller and smaller? It's going to get lower and closer and closer and closer to the tangent line. Can I ever have h actually hit 0? Nope, but I can approach. And that makes the mathematically impossible plugging in there being no distance. Can I get to my picture? Plugging in there being no distance. If I were to plug in h is 0, that'd be 0 over 0, keep going. That doesn't work, but the limit says, oh, I can do the impossible. Even though you can't actually solve 0 over 0, keep going. If you just put a limit in there, we can get there. Now let's go ahead and get rid of this. This is just showing us getting closer and closer and closer. It's in the book if you want further clarification. There are even some apps that let you see this getting closer and closer and closer and how the slope gets closer and closer and closer to a tangent line, like what we were doing with our tables. But here's the long story short. To find any slope of any graph, linear, curved, quadratic, or otherwise, all we need to do for the slope of the tangent is solve that snazzy limit that we just practiced solving. So the slope of the tangent, which the book just calls m, the slope. The slope of a curve is the slope of the tangent, and the slope of the tangent is defined to be this little guy called f prime of x, which is found by the limit as h approaches 0 of f of x plus h minus f of x all over h. And this whole idea could be called the description or even the definition of, new vocab word, the derivative. Now you guys have sometimes heard the word derive or derivative in like common language having to do with very non-mathematical things, but in math, the derivative is very, very, very specifically talking about the slope of a tangent line, which can be applied in so many different ways I can't even begin to say. But the derivative is this little guy called f prime of x, who can be solved with this little guy, the limit of the difference quotient. Is this a yellow box? Yes. Is this an important yellow box? Yes. Does the formula that should probably make it on your formula card for the final? Yes. But is this really just the exact same thing that we were just practicing in 47, 48, 49, and 50? Yes. Just now it has a spiffy name of a derivative, and now it has a spiffy application of, hey, that's how you find the slope of a tangent line. And if you want the slope in general, then you just leave it with x's, like we saw when we just solved number 48, 49, etc. Or we didn't solve 48, 49. We solved number 50 in an example. But if you want to find a specific slope, then what you're going to do is just at the very, 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 very end, when you've got something like 2x that we saw a little bit ago, is you would plug in whatever x they give you. And so to end today and to finish off our new content, how would we find the slope at this point? We would take this point and we would say x equals -2, and we would store that away as a clue that we'll use much, much later. But to do the problem, we'd actually just say, well, we have this very special formula that says it's time to take a limit as h approaches 0 of f of x plus h minus f of x all over h. And when we take that limit, yes, I did it all at once and didn't write f of x plus h separately. But if you didn't kill a puppy, and if you properly simplified, and if you kept going because you knew you should, and if you solved at the very, very end by plugging in 0, you just wouldn't stop. Go one step further. And you would say, hey, wait a minute. Don't I have an x? So maybe shouldn't I plug it in? Answer would just be one extra baby step. I'm going to narrow down your homework and make it shorter. You guys are going to practice the limit, the special limit, and then you're going to practice just calling it a slope. Bye, guys. I'll see you tomorrow. Practice up so that you're not a dead weight to your group. And let me narrow down your homework.